Hi, afternoon everyone. We'll be starting class in 1 to 2 minutes time. To answer the question in the chat, some of the problems that you're going to be encountering throughout the entire lectures are going to end up using those approaches. So you'll get practice on them regardless. And when you get to your group assignments in particular, you might get some practice problems regarding those. In the meantime, if you are looking for practice problems regarding those approaches, I would suggest that you look for common recursion problems in particular. And you want to look for the problems and solutions, see about how do we go about finding the solution and seeing the approach that they take in solving these problems and how they go about formulating the solutions themselves. Alright, good afternoon everyone, and today's lecture is going to be based on the topic of space and time complexity, which is going to be our longest topic for this course in particular. The reason being is that space and time complexity, when it comes to the performance of your programs, is actually quite important, especially for determining how much memory your program uses, how fast your program can operate within a given set time. And we won't be watching how do we analyze this with respect to the code written to determine the performance of a program in regards to space and time complexity in particular. One thing that we will note though is that the focus in this lecture is going to be a little bit more on time complexity than space complexity, but we will discuss space complexity as well for us to see, okay, how can we actually formulate the equations that represent space complexity of an entire program by watching how much memory you can physically take. Alright, so let's get started. So the notation that we're going to be using for space and time complexity in particular is going to be what we refer to as the big O notation. And for any programming interview, it is important that you know how to use this notation to represent your space and time complexity of any given example code that may be presented to you during any sort of programming interview. It's also quite important to know that if you wrote a more efficient algorithm versus a less efficient algorithm with respect to your code itself. So let's start with an analogy before we actually get into a physical problem with regards to the code. So if we do have a file on a hard drive and we need to send this to a friend across the country as fast as possible, which one of the two ways is going to be faster? Now, the first thing you might say, well, okay, it's more convenient to do electronic transfer via the internet. And that's true if the file is small, but if the file is extremely large, then what would be the most efficient way to transfer this? What about if there's a high urgency on getting the file, and what if you have to manage a cost of transferring the file as well? So these questions come into play when you start thinking about your complexity analysis, as well as if your code is going to be more efficient or less efficient. So you need to keep in mind these sort of questions that's going to be asked when you're going to be faced with space and time complexity. So the runtime, the time complexity, is what we refer to as big O time. And mapping this to each one of these methods here, if we say electronic transfer here is O of S, where S is the size of the file, this means that the file size increases, the time also increases linearly. However, if you're physically delivering the file, meaning that if you took the file on some portable hard drive or a flash drive, and then you jump in your car, you go across the country, and you reach your friend's house and you give it to him for him to offload, the time that's going to take is going to be O of 1, where 1 basically represents a constant, meaning that even though if the file increases or decreases in size, it will not take any longer for this file to reach to your friend, because it's going to take the same time to load on the hard drive, and then jump in the car with the hard drive and go to your friend, and then reach by him and offload it on the hard drive and so forth. It's just going to be the same time no matter what. Now, if we graph this, O of 1 here being a constant, is going to be a horizontal line here, because it's going to take the same time no matter what for your file transfer. And O of S here is going to be linear with a constant gradient. And one thing to note here is that no matter what this gradient here is going to be for O of S, at some point it's always going to exceed O of 1. And that exceed point is where you know, okay, O of S is no longer efficient and you should be really doing an O of 1 algorithm instead, or O of 1 method instead, to get your file across in the most effective way possible. Now, besides O of S and O of 1 that we just now saw here, there are many more runtimes that do exist, and typically we use the n notation for these runtimes. So we get like log of n log of n squared, 2 of n. In some cases you might get square root of n. You can get really weird mathematical notations for your order of n, and it's possible to have any one of those mathematical notations to describe your time complexity order of n for an algorithm. And there's no fixed list regarding this. It can be any mathematical notation that you can think of. Now, the mistake a lot of people make is that they think, okay, because the notation is always with respect to n, that means all notations need to be with respect to n when it comes to space and time complexity. Now that's wrong. It's possible to have multiple variables in your runtime because those variables behave differently from one another. So, for instance, like our example here, if your time to terminate the fence is going to be w meters high and w meters wide and h meters high, we can map that length and breadth here with respect to the time, and we can say that's going to be order of w of h. And then if we add another layer on top of that, meaning that you need p layers of paint, meaning how many times you need to repeat this, then your complexity becomes O of WHP, where these variables here are multiplying with each other because they compound with one another accordingly. Now, there are different notations that you may encounter regards to the big O notation. There's big O, which is going to describe the upper bound of the time. There's big omega, which describes the lower bound of the time. There's big theta, which basically describes the two above that, and is referred to as a type bound. And you may see all these three here and in textbooks and whatnot, but for all purposes and for interview purposes, we're always going to be using big O here. That's going to be giving us the tightest description of the runtime. So we don't care about capital omega, we don't care about big theta, and so forth. We're going to be using big O notation to make things simple, and we're going to be using it to get the tight bound on the runtime. We want to see why this is important, because the upper bound and the lower bound of the runtimes you want to see throughout this lecture, it's not going to be very important whatsoever. Those are going to be some extremely rare cases when you do happen to get the tight bound on the runtime, which is also referred to as your average time, is going to be the case where that's going to happen the most regarding for when your algorithm or your code runs. Alright, so before I continue, are there any particular questions regarding the analogy or the notations that we just saw here? Big O basically describes the average time for which your algorithm is expected to run for most of your cases, regardless. And you're going to basically see that throughout the entire lecture, when we start with code examples, why this big O is going to be important regardless. There's also some cases where you end up using the big O notation to describe how much space your algorithm takes, how much memory you are going to allocate as well. But the importance is to see how well is your program optimized, because you want to see if your program can perform as fast as possible, as well as use the least amount of memory possible, instead of it like taking extremely long to execute and using too much memory. So this notation is a very important notation to see in how effectively you can write your algorithm or your code to have the best possible performance in regards to time and space. Right, it doesn't seem like we have any further questions regarding this, so let's move on with the lecture. We're going to use a practical example here before we actually go about describing these, and this is going to be defined as the best, worst, and expected cases. So if we have something that we refer to as a quicksort algorithm, which we're going to be actually learning about in 2 weeks' time, the general gist of this is that it's going to pick a random element in the array, and it's going to use that as a pivot. And anything that is less than the pivot, it's going to put that in before that in the array, and everything that is greater than the pivot is going to put that after that in the array. So just to illustrate what this looks like, let's say we had 2, 3, 10, -1, 6, and 5 here. And let's say we choose 5 here as our pivot. So anything that's less than 5, we're going to put to the left of it, and everything that's greater than 5, we're going to go to put it on the right. So we can say, okay, 5 is here. So we start with 2. 2 less than 5, so we'll say, okay, yes, that's 2. I'm just going to put 5 here. Then we check 3, that's less than 5, yes. We check 10. 10 is going to be greater than that, so we put 10 here. -1, less than that, yep. Then 6, that's greater. And we basically finish at that point. And then we choose another value and we keep on the pivots and so forth. But that's basically the gist of how the quicksort algorithm runs until it sorts out all the values in its proper order. What we're going to look at in particular is what's going to be our best, worst, and expected cases for this sorting, as it keeps on repeating until we get the entire array here sorted from the least value to the most value here in particular. So the best case regarding this algorithm is that we only have to do this once, meaning that we get extremely lucky and we find the middle point on our first pivot when we select this, and everything less than that pivot is going to be in order, and everything under that's greater than is also going to be in order as well. So we only do this once, and we refer to this order here as O of n, where n is the number of items in the array. So we only transverse through all the items, which is n items, and we define this as O of n, in the best case. The worst case is that we don't traverse the array once, and each time when we choose the pivot, it's always going to be the biggest element in the array. And we will never get that nice division of elements across the pivot. It's just going to be like all elements are going to be skewed onto one side of the array, because that's going to be the biggest element in the array, and that biggest element is just going to be on the right hand side all the time. So in that case, the runtime is going to be O of n squared, because we're going to be doing n times to sort each one of those, multiplied by n times for the repetitions of the sorting. So we get O of n squared as a result. Now, best case and worst case are extremely rare, and we don't really watch these in particular because they're not very important. The expected case, which is what's going to happen most of the time, is what we refer to as a runtime of O of n log of n. And I'm not going to explain why it's O n of log of n at this point. I want to come back to this. I want to see if you guys can actually formulate why it's going to be O of n of log of n. And it would be a worked example, yes, but what's going to be important here is not getting towards this final answer, but your approach as to how you formulated the result here. And that's what's going to carry the most marks regarding your assignments and your quizzes in particular. So just to repeat what I just said, best case time complexity, it's not very useful. That's going to rarely actually happen, like once in a blue moon or something like that. And in most cases, your worst and expected cases are going to be the same. Sometimes they're going to be different. When they are different, you actually do have to specify what they're going to be. But most of the time, you can just have the expected case, which is going to be the average case, and you'll be pretty much okay with that regardless. So we're going to be paying attention to this in particular while we start with code examples to see how do we formulate this expected case. Now, space complexity is also important because that determines how much memory your program uses. So what we observed there before was time complexity, seeing how fast your program was going to run. But with space complexity, we still use the same O notation, but the n here is no longer capital, it's just going to be column. So we use common variables instead to represent your space in particular as well. Unless otherwise stated that, okay, we're going to be like, this is time complexity and we just happen to use common variables, that's perfectly fine as well. So, in our general example here, if we create an array of size n, because it's n variables that needs to be stored in the array, that's going to be O of n space. If it's a two-dimensional variable of size n by n, that means it's going to be O of n squared space. Now, similarly, that's how we just now saw here, that you can have multiple variables representing your order. If our array here was size n by m, the space complexity is going to be O of n m, because n and m are distinct in nature and there's no relationship between the two of them. So once there's no relationship defining these variables, they are going to be treated as independent of one another, and you have to list them out accordingly in your order or your big O notations here. If they are related, you can reduce them down into one single variable and you can just get away with like O of n and so on. But so long as there's no relationship between the two of them that you can prove, they have to be independent of one another and they will be stated in the order notation as follows. Now, space complexity plays a very important part when you start writing recursive functions, because as we saw in last week's lectures, recursive functions, whereas they do take up less lines of code, they use more space or more memory in particular because of the repeated function code. So let's observe why this is going to be important here by watching a simple recursion function here for the sum, where we have return n plus sum n minus 1. Now, this code here will take O of n time regardless, but let's see why it's going to take O of n space in particular. So each function call here is going to add a level to the stack. And the stack here is basically, you can think of this being your memory allocation on your computer for the program. So if we said n here started at 4, we'll go sum of 4, then because it's n plus sum of n minus 1, this here is going to be sum of 3. Then it repeats, so we go sum of 2, sum of 1, sum of 0. Each one of these instances here means that you need to have your n allocation here for each one, and it's going to be repeated for each one of those function calls. So for sum of 4, we have its own instance here of insum. Sum of 3, because of the recursion function, we then have its own instance where n is equal to 3, and so forth for 2, 1, and 0. So each one of those function calls there has its own memory allocation because of recursion. And that's why it ends up taking O of n space accordingly, because we only have to deal with one variable here being n. So this will be n equals 4, n equals 3, n equals 2, n equals 1, n equals 0. And because n goes from 4 to 0, it takes up O of n space accordingly. There are some cases where you may have n calls, but that doesn't mean you will end up taking n space or O of n space. And this is particularly true for iterative functions. So if we have pair of sum here, meaning that it just returns a plus b, and if we call this function here in an iterative function, meaning a for loop, yes, this here, we see the for loop goes from 0 to n. There will be O of n calls to this pair of sum function that we see here. But these calls don't exist all the time on your memory stack, because the function here is iterative in nature, not recursive. So each function call here, once it does find its results and it stores it in sum here, it means that the function is finished executing and it doesn't rely on any other previous or future values, and it can just exit here accordingly until the next iteration in the for loop. So because the calls do not exist simultaneously on your call stack or memory stack, you only need O of one space for this function call each time it is called, until it goes out of scope of the for loop here. So yes, there will be O n calls to pair of sum, but the space required for each instance when pair of sum is called here for each iteration in the for loop is just going to be O of one space. Anyone confused about this? Ask now. A for loop here. So for each instance of the for loop, so let's say when I is equal to 0 and we go pair of sum 0, and then this is here is going to be 0 plus 1, so that's 1. This only calls once for this iteration here. And once it finishes and it returns the results, it no longer needs to keep this function here in memory. So once we reach the end of the for loop here, it releases this memory for pair of sum accordingly. On the next iteration, it uses back the same memory location that you make, for lack of a better analogy, that was previously allocated to pair of sum. It just reallocates it back here accordingly as well. So it never adds more memory, it just keeps on reusing the same memory for each one of those function calls. And that's why it's only going to take O of one space here accordingly. The function here, because of the for loop, and we see it starts from 0 up to n, yes, there will be O of n calls to this pair sum function. But because this function here is not being called recursively, and each function call does not depend on another function call and so forth, it just keeps reusing the memory here accordingly. So that way it's just only going to be O of one space for each iteration here in the for. Whereas in our recursion, because we are dependent on the function being called by itself, that means that we need to allocate memory for each one of these functions here in order to get up to the final results for our recursion. The for loop here, we can use the same memory that's being allocated for pair sum for each iteration of the for loop itself. So we just use the same memory and we keep on reusing it together. So that's why it's going to be O of one space. And yes, it's because the recursive functions end up using the stack. Your iterative functions, because the function calls just basically reuse memory, it doesn't have to be on the stack accordingly. So in short terms, remember, because recursion keeps on calling itself, that means you have to allocate memory for each one of the function calls to recompute back up to your final answer. In iteration, this isn't the case. Each time when you call the function here inside the for loop, it just reuses the memory accordingly. Because once you hit the end of the for loop here, meaning this curly bracket, and you go out of scope of it, it just releases the memory accordingly until the next iteration. That same memory that was used from before is just reused again for your iterations. So that's why it only uses O of 1 here accordingly for regards to the space. So recursion uses more memory, iteration reuses the same memory. Alright, so any further questions regarding this? O of 1 is better than O of n because we just now saw that in our analogy in the start. Because O of 1 is a constant, O of n is basically a straight line with a constant gradient. And yes, there are some cases where O of n is better than O of 1, but if they do happen to start at the same point, that's going to be the 0 point, O of 1 will always be better than O of n. And just to draw this out for you, what I mean by starting at the same point is if we actually physically drew this graph here, and this here is n and this here is t, n being the space, t is the time. O of 1 here will just be like that. But O of n here, if it starts at the same point here, will be like this. So we end up using more space regarding it, and more time regarding it as well. Sorry, I said that wrong. We end up using more time regarding it in particular. Because this axis here is O of n axis, not the n axis. Sorry. So yes, O of 1 is just basically a constant time, O of n is an increasing regardless. Alright, nice. Doesn't seem like there are any further questions, so go on ahead. So there are cases where the O of n code will run faster than the O of 1 code. And we saw that in our analogy at the start of our lecture, where the start point for O of n was less than the start point for O of 1. But this only happens for very specific inputs, and like I said, it's kind of rare for that actually to happen, because those are some extremely rare cases for the lecture. The big O notation just basically describes the rate of increase with respect to time or respect to space. And if you do have some constants at runtime, let's say that was O of n plus 2 or O of 2 over 3 and whatnot, we just drop those constants because they don't add any value in describing the efficiency of our algorithms. So for instance, like if we had O of 2n, this 2 here doesn't really add much value. So because it's already linear in nature, we just say it's O of n, because we're just describing the rate of increase. We don't care how much it is increasing by, or how much it is decreasing by. Once it is linear in nature, it's going to be O of n. If it's quadratic in nature, it'll be O of n squared. If it's cubic in nature, it'll be O of n cubed. If it's logarithmic in nature, it'll be O of log n, and so forth. We just care about the nature of it. We care about the specifics when we're using big O notation. Now, here's a teaser for you guys. Which one of these codes here is going to be faster? The code on the left or the code on the right? And I want to ask this question here. Apple. let's see what you guys think. Alright, let's give it a 30 seconds again and see if there are any last minute votes coming in. Alright, so voting has ended at this point, so let's wait for the results to pop up here in the chat. Looks like. So the majority of you thought that the left-hand side code here is going to be faster than the right-hand side. And when I guess the minorities here also thought that the right-hand side is going to be faster than the left-hand side. And then we have an extreme minority here who thought that it's neither. So the extreme minority here is right. Neither of these are faster than the other. And I'm going to explain to you guys why neither of these are faster than the other. They actually do take the same time. So this X here for our array on the left hand side, if our array here was size of n, that means that this loop that we see here is going to run n times for each one of those elements. The checks here are just going to be 1 and 1 here, basically to say, okay, it's checking these 1 for each one of these instances. And then if we multiply each one of these together, it's going to be O of n by 1, which is O of n. Alright, simple enough. This here is done n times as well, and this here is also done n times as well, right? This here is done once, this here is done once. So if this is done n times, and this here is also done n times as well, you may say, okay, that's O of n plus O of n. I'd be like, okay, that's 2 O of n. But no, this is where actually your analysis is actually going to be wrong. So let's restart this. I want to show you guys why it is wrong. So we know here that the loop here is going to run n times, right? So n times for this loop. But we're not going to be watching this. we're going to be watching what happens inside the loop. So this here, this check is going to run n times, and this check here is also going to run n times, right? That's n plus n equals to 2 of n. Similarly, when we watch on the right, these loops here run n times as well, but we don't care about those. We only actually care about what's going to be happening inside there, right? So this actually runs n here, and this runs n, but we need to add the two together, and that's going to be n plus n equals to 2n. And that's why neither of these codes here are faster than the other. They do take the same amount of time, regardless, because we are watching the instructions that actually do happen inside the loop. So even though that you do have a repetition of the loop twice, and each one of those has a single instruction, regardless if we had the loop and the instructions, we have two instructions inside the loop, it's going to take the same amount of time no matter what. And we saw the mistake at the start where we say, okay, the loop runs n times, and then each one of these runs once. So we say, okay, that's O of n, and then we saw that on the right hand side, it's like O of n plus O of n. That's the wrong way to actually go about doing the analysis. You want to actually see what happens inside the loops here and how many times each one of these instructions are called with regards to. That's how we got 2 of n here, and then we got n here and n, and we add those two together, and we also got 2 of n. So they do end up taking the same amount of time, regardless of what happens. So remember this particular mistake, and it's common to make this mistake, and not to make this mistake for any future analysis. That way you can get across this and know how to actually do the analysis properly. We also have to accept that in some cases, O of n being a linear time coefficient here is not always better than the O of n squared coefficient, which is going to be the quadratic relationship here. And the reason for this being is that once you go down to the number of instructions that we just did here, in some cases you will have to end up going down to the assembly level. And when you go down to the assembly level, which is like all the way down to machine code, multiplication operations in particular, when you go down to machine code, they do require a lot more instructions than addition. And your compiler hides this from you because it does a lot of optimization. So we don't really care about all this machine code. It's horrendously complicated, and we're not really going to be focusing on this. We're just going to be watching it at our C++ code level, and we're going to be using our analysis for our big O notation with regards to time and space complexity at this level only. We will not be going out to the machine code level. Things get very horrendously complicated. The one thing to note though is that multiplication operations, they do require a lot more instructions than adding two variables together. What about if we have expressions where we have n terms adding to each other, or maybe subtracting or some other sort of fashion, right? If it's going to be O of n squared plus n here, this plus n is not a constant, but it's also not very important, because the n squared here takes priority. So we just shorten down the order here to O of n squared, because this plus n, it really doesn't add much importance to the order or the behavior of the code. You also can drop other things as well, depending on which n term here takes superiority. So in O of n plus log of n, a linear relationship here takes precedence over a logarithmic relationship. So you just describe this as O of n. In this complicated equation here, we have 5 by 2 of n, 1000 n to the 100. This actually is just going to be O of 2 of n. And reason for this being is that n to 100, if n is 0 here, that's just going to be 0. If it's 1, it's just going to be 1, and so forth. This here will just end up being some sort of constant point, even though we have n to the power 100 here. The 2 of n here actually takes precedence for the entire equation, because this is going to be leading or superior order throughout the entire thing. Similarly, if you have two different variables where the variables do not have a relationship between each other, you will actually have to state out those variables for your order. So, for instance, if B and A here have no relationship between the two of them, you leave the order as is. So it's going to be of B squared plus A. That cannot be reduced, that's your final answer. And determining which terms are dominant, it's very simple. Just graph the terms. And whichever one tends towards infinity more than the other, it's going to be the more dominant one. So for instance, x of factorial here is the most dominant term for all of these, followed by 2 of x, x squared, x log of x, and then O of x. And then O log of x is the least dominant here, accordingly. There are horrendously worse runtimes than any one of these that you're seeing here on this graph. And I'm inviting you guys to actually go and look up for these horrendously worse runtimes. A good idea of something that you can look up, even though it's not very horrible, you may want to check up what's going to be the order for the square root of n. Because I did make a mention of that at the start of the lecture. That's something you might want to investigate. Alright, so that brings us to the end of our first lecture, and what we saw here is that with regards to describing the effectiveness of our algorithm or codes, we're going to be using the big O notation to describe the time and space complexity. We saw that for time complexity, this depends on how your code runs, whereas with space complexity, this depends on how much memory your code actually uses. We also saw that when we're doing the analysis for the complexities, and in our particular case, the time complexity, we go down to the instructions that are being executed to know how many times these instructions are being executed instead of looking at it from the loop level instead. Because the instructions is what actually is going to be played in the important part of how many times the program executes these instructions to determine which code is going to be faster or not faster, or both of them take the same time regardless. With space complexity, we saw that the difference between recursion and iteration, recursion uses more memory for each one of those function calls, whereas for iteration, it reuses the same memory, thus being more efficient regards to space complexity. We also saw that depending if you have multiple n terms in your order, you always choose the dominant or superior n term just to describe the space or time complexity of a particular algorithm or a particular piece of code. The other non-dominant terms don't really add much value because you're just describing the overall behavior of that code. If, for some instance, that you have multiple variables and there's no relationship between the variables, you are expected to state these variables in your order notations. So, for instance, where we had the fence, that's W meters wide and H meters high, that order is going to be order of WH. If we were adding P layers of paint, it's going to be order of WHP. Similarly, if we had an order of B squared plus A, and if there's no relationship between B and A, just leave the order as is because it cannot be reduced at any point in time regardless. Alright, so are there any final questions here at the end of our first lecture before I go on into our second lecture? You might want to explain what you mean by your accent if n can only be order 0. I mean, like, if it's going to be order of 1 or order of 0? Or do you mean n being the number of terms? this time complexity graph here on this slide? Alright, okay. So n here just basically describes the relationship of regarding how your order operates. So if your code expands linearly, we say O of n. If your code expands quadratically, we say O of n squared, and so forth. It's just basically describing the relationship of how your code operates with respect to time and space. So let's say for your array, you have size of it being n, and you have to go through each one of the elements in the array. That's going to be such that it's going to be that because you go through each one of the elements, that means you go through the array n times, so that's going to be O of n. N can take any value. So n doesn't have to be only 1 or 0. N actually can be any value. The only reason why we have O of 1, and we use that 1 there in particular, is just to describe a constant. So when we actually have O of 1 here, this here being O of 1, you can have like an O of 2, an O of 3 here, and so forth. But it doesn't really add much value when you say O of 2 and O of 3 and so forth. We just say O of 1 because we know that's going to be just a flat horizontal line with no gradient whatsoever. Because it's just going to be a constant value throughout the entire process no matter what. No matter how much n increases, it will always take the same amount of time no matter what. That's what we're seeing here. N can take any value, but if it's O of 1, it's not affected by n. If it's linear, that means that as n increases, t also increases by n. Meaning that the time for the algorithm operates accordingly with regards to as n increases. So that's why we get that linear relationship. It's like saying if you have to sort n items, and let's say if it was just only one item, you take 1 second to sort this. But if it's 2 items, you're going to take 2 seconds. 3 items, it takes 3 seconds. 4 items, it takes 4 seconds, and so forth. You get that linear relationship by getting that description, because we know that the gradient here is going to be 1. And when you go up to n items, it takes n seconds. So that's how we get O of n. So it's just a nice way to describe the relationship of how long your algorithm will take with respect to the amount of items you're dealing with in the code. So for instance, we had O of 2 of x here. Well, I would say x here was just basically n. As the number of items increase, being n being the number of items, the time it takes is going to be 2x time in order to go about doing its operation. So let's say if you had 1 item, it's going to take 2 seconds here. If you had 2 items, it will be 2 to the power of 2. It's going to take 4 seconds. 3 items, it's going to be 2 to the power of 3, so it ends up taking 8 seconds and so on. So the order here just basically, or the O notations, describes that relationship between the number of items versus the time it's going to take. Similarly for x squared, well, like I said, if x was n, we had 1 item, it's just going to take 1 second because that's 1 squared. If we had 2 items, it's going to be 2 squared, which is 4 seconds. If we had 3 items, it will be 3 squared, which it takes 9 seconds, and so that's how the relationship operates with regards to it. So it can typically be like saying, yeah, y-axis here is time taken, And your x-axis here is number of items. The time taken here is going to be O of n, and the number of items here is n. In this case, because it's with respect to x, it's going to be O of x, and this here will just be x. Right. Any further questions? Alright, doesn't look like we have any further questions, so let's move on to our second lecture for today. Taking annotations. Alright. Yeah. Alright. So in our second lecture here, we're just going to expand a little bit more. Yeah, ask the questions, interrupt when you're ready. In our second lecture here, we're going to be looking at different ways of how we actually go about analyzing our orders here with respect to different operations and how do they compound in regards to how we formulate our orders here. Yeah, like I said, if you have any questions, feel free to interrupt. I'll address them accordingly once I see them in the chat. So as I said, feel free to go about interrupting me when you're ready. So if your algorithm is particular, and that's what we're going to be observing here in regards to a code to figure out how do we formulate the order here using this. So in adding runtimes, this is when we have independent loops here that do not nest within one another. So if we have a loop here doing A times of work, and then a loop here doing B times of work, or B chunks of work, the order for this loop alone is going to be O of A. And then the order for this second loop here is going to be O of B. And then when we compound the two to say, okay, for this entire program here, what's the general full order? It's just going to be O of A plus B altogether. That seems very straight and forward and simple, right? So that's when we add runtimes together. You multiply runtimes when you have nested loops. Because the outermost loop here is going to be responsible for the iterations tracked when each case here in B is completed, these two here multiply by one another. And to give you an idea of this, let's say array A here had 3 items, and array B here had 2 items. And we know arrays here, it's going to start from 0, so 0, 1, 2. Let's say 0, 1. When array A here is at 0, array B here will be at 0, but then it's still at 0 here, and it goes 1. Because that's how the rotations will run. So this innermost loop here must run before the outermost loop here iterates. So the innermost loop must complete all its iterations before the outermost loop iterates by 1. Then we'll go 1 here, 0, 1, 1, 2, 0, 2, 1, and then we complete. And we see here, this is 1, 2, 3, 4, 5, 6 steps. Which is basically, if we took these two values here, and we multiplied the two of them together. So, for nested loops, it's going to be that you multiply the orders together regarding each one of these. So, this for loop here, the outermost for loop is going to be O of A. Innermost for loop here is going to be O of B. But because they're nested, multiply the two together. So it's going to be O of A by B or O of B by A. Multiplication, the arrangement of variables don't matter. It's going to be the same thing regardless for multiplication. Same thing with addition. The order of the variables don't matter in this case. So the general rules is that so long as your algorithm is like do this, and when you're done with that, you go on to some other operation, you add them together. But if it's that you need to do this for each time you do that, then you multiply the runtimes together. And the nice way of thinking is that if you have for loops that do not nest with one another, so you have a first for loop here and then a second for loop afterwards, they add together. But if you have for loops that nest within one another, then you multiply them accordingly. It's very easy to lose track of this in any sort of interview. Be very careful when you're doing the analysis here. It's also very easy to lose track of it in any sort of code as well. Do the analysis very carefully when you sort of problem. So there's also dynamically resizing arrays, and in programming terminology they refer to as array lists. And they're better than static arrays because, like the name says, they expand and contract with its size. Now, we're going to be observing the order of this when, let's say, an array, let's say, hits capacity and it needs to expand itself. So for this particular instance, let's say the array list hits the capacity and it needs to add another item. We're looking at it's going to be creating a new array with double the capacity, and it copies all the elements from the first array list into the new array list. We want to be thinking, how do we describe the runtime of this insertion that actually occurs? That's what we're going to be observing here. Now, this is tricky because we don't know in certain cases if the array was full. So if the array was full, up to n items, for each insertion of the element into the new array, that's going to take O of n time. We also know that when we create the new array, it's going to be twice that of the original size. That's going to be 2 of n. It has to copy those n elements over into the new array. So that means that entire insertion will take O of n time. However, for each one of the elements, note, for each one of the elements, this is going to take O of 1 time. So, in trying to describe all of these operations here, there's a terminology known as amortized time. Because there's a worst case that may happen, but we try to figure out what's going to be our average case. So when you try to incorporate the worst case and the average case, knowing that the worst case will happen at some point, but it will not happen for a very long time or a very long instance, we refer to this as amortized time instead. So let's see what's going to be the amortized time here for our dynamic array for this particular situation. So As the elements are inserted, we can double the capacity of the array when the size of the array here is a power of 2. We just use this for simplicity's sake, just to explain our relationship, say, for amortized time. So each time when the array is doubled, it comes like if we had 1, 2, then 4, 8, 16, and we keep on going up to some unknown number x, right? And if we try to sum 1, 2, 4, 8, 16 going all the way up to x, you find that it's going to be a little bit tricky to try and sum that. So what if we did it in the reverse order? See that instead of increasing the array, we downsize the array. It's basically the same thing that we're doing, just in the reverse. Oh wait, it's in reverse. So we'll have like from x, then we go x of 2, x divided by 2, then x divided by 4, then x divided by 8, all the way back down to 1. And it's easier to sum this, because this roughly here is just going to be 2 of x. So because we know that it operates 2 of x in the reverse, that means going forward, it's going to be operating 2 of x as well. Because it's just a reverse in direction. So those x of insertions that we saw there, it's going to end up taking O of 2x time. And the amortized time for each insertion is going to be O of 1. So the amortized time for x insertions is going to be O of 2 of x. But for each insertion, the amortized time will be O of 1. Right. Any particular questions regarding this? Amortized time is basically a way for us to describe the average case of your expected runtime of your algorithms, where we also factor in that the worst case will occasionally happen as well. In some cases, your average case and your worst case expected runtimes are the same, but in cases when they are not, we describe this using amortized time instead. This is an instance where the worst case and the expected case do not have the same runtimes, but their worst case will happen occasionally. So we need to describe this using one term, which is going to be referred to as amortized time. All right, any further questions? It doesn't look like we have any further questions. Let's move along. Now, we also saw that there was an order of log of n. But where does this order come from? And this order basically comes from when we start looking at what we refer to as the binary search algorithm. So the binary search algorithm is like if we're looking for an x value here and some n elements sorted. So remember the array here is already sorted. This x element being what we are searching for is compared to the midpoint of the array. So if it's the middle, meaning if it's the same midpoint, we're just going to be returning that. If it's less than the middle, we just search for the left-hand side of the array. And if it's more than the middle, we search on the right side of the array. And we keep on repeating this as we keep on going on until we actually find this x value. Yes, this topic is going to end up coming for a quiz in particular. It actually will be your first quiz. Don't worry, the Wednesday session is tutorials, so we get a lot more practice regarding these topics and regarding how to analyze the code, so figure out what's going to be the orders. And next week, Monday, in particular, we also get more practice as well, seeing how we analyze the orders for more complex code and so forth. So I'm not leaving you guys hanging. You actually are going to get practice in the tutorials regarding the analysis of codes and figuring out what's going to be the time complexity for each one of these. So just to reiterate our binary search, if we're looking for some element x here, where we know x is going to be the value, if we compare this to the midpoint of the array, where the array is already sorted from least to most. If it's the midpoint, meaning middle, just return because we already found it. If it's less than the middle, we search the left side of the array. If it's more than the middle, we search on the right side of the array. And we keep on repeating this as we keep on going up. So our example here is like, if x here was 9, and we need to find 9 here in this array of values that's already sorted from least to most. The midpoint here for our array is 11. So we compare x being 9 here to 11, and it's going to be smaller. So at this point, we shrink it down so that we're only focusing on this left-hand side of the array. This here being our left side of our array. We choose the next new midpoint here. And we do the comparison. So comparing the midpoint here to our search value, or x value, we see that it's bigger. So then we just only focus on this side of the array instead. Now, we already checked 8 here, and we know that, okay, it's bigger, but we only have 2 values here. So we don't need this part here anymore. We just only compare to the 2 values. There's only 2 values here, there's no midpoint. So we just choose to see which one is going to be for 9. And we compare 9 to 9, and we just return to get to our value. So the binary search operates such that it keeps on halving the array until it finds its value accordingly as of such. Now, how does this compare back to our order of log n runtime? So let's actually observe this. So we started off with that n element array to search, and then we have that n elements, depending on if x was on the left hand side or the right hand side, down to n divided by 2. If we still don't find it, we have that half that we just don't had it, and we are down to n divided by 4 elements. And we keep on having, going down the road until we stop where we find the value, or we are down to only 1 element where that absolutely has to be the value. So this is really that we keep on doing a sequence of divisions by a constant factor. So if our array was 16 here, and we divide by 2, we went 8. Divide by 2 again, it went 4. Divide by 2, it goes 2. Divide by 2 here, we got 1, and we keep on going. Right? If we did an operation, it's just like if we kept on multiplying by 2, keeping on going up. So 1, 2, 4, 8, 16, and keep on going. So this k expression here to map these multiplications, and then we want to see how we would map it back to divisions, is that we will be 2 of k equals to n here, where n is equal to the size of our. So 2 to the power of 4 here will give us 16, where 16 was the size of our array. And if we decide to write this as a logarithmic formula instead, this is going to be log 2 of 16, which will give us the value of 4 here, our power. So we can say log 2 of n here, because 16 was the size of our array, equal to k, which maps back to 2 of k equals to n. So whenever you see a problem that where the number of elements are going to be halved each time, this is going to be a O of log n runtime. Conversely, when you see a problem where the number of elements is doubled each time, this is going to be of O of 2 of n runtime instead. Just going to write this on the slide for you. So if the number of elements is doubled, there's a chance that it's going to be O of 2 to the power n for your runtime instead. But so what happens if we have different cases where it's not half, if it's divided by 3, divided by 4, divided by 10, or some other thing like that? For the purpose of our big O notation, it's not important. We're just describing the behavior of the time complexity or the space complexity of our algorithm. And the different bases of the logs, they're just only going to be off by a constant factor. And this is seen by the conversion of logs equation that I'm giving. So if we had log 10 of p and we wanted to get into some other base, where the other base here is going to be log of 2, there will be log 2 of p here divided by log 2 of this 10 base that we just know about here. And because of this relationship, because of the conversion of log equations, it's just going to be off by that constant factor once we actually do the calculation as such. So we just keep things down nice and simple. So log 2 of n, or in particular cases, we may say like order of 2 to the power n and so on. But we want to see why we can't do this for powers in the next slide. For logs, we can just keep everything down to log 2 of n or log of n regardless. Oops, no, not in the next slide. So the reason why we can't do this for powers is because when you watch the graphs for powers here, being like if it was 2 of n, and 3 of n, and 4 of n, each one of these here, they do not differ by a constant factor. So you can't do this for powers. You still have to specify, you still need to specify if it's going to be of 2 of n, or of 3 of n, or of 4 of n, and so forth. However, for logs, we can get away with this because of the conversion of log formula here. So you can specify everything back down to O log 2 of n, where you can just say O log of n. That's perfectly fine. But remember, for powers, actually going to have to specify what the power is. 2 of n, 3 of n, 4 of n, and so forth, because it's not going to differ constantly. So let's go back to our Fibonacci code that we saw in earlier lectures, and let's actually see what's going to be the runtime of this. We're going to go back to our recursive tree here, and basically you saw two function calls here, f of n minus 1 plus f of n minus 1. Actually, this is going to be f of n minus 2. Correct this on the slides. Because that code there is wrong. Correct that accordingly. So you may see those two function calls there, and you think, okay, it's going to be O of n squared. And no, that's wrong. We're actually going to have to analyze the recursive tree here. We saw in our previous lectures to actually figure out what's going to be the runtime of code. So how many orders actually are there in the tree here? Sorry, how many calls are there in the tree? And we don't actually need to count to figure out how many calls actually are going. The reason for this being is that let's just watch f of 2 here. F of 2 here has two function calls, right? And then if you watch f of 3 here, there's 4 and 2. So if we watch f of 4 here, that means it's going to be 8, 4, and 2. What the pattern? So the tree has n depth, meaning the number of levels. So this is level 1, level 2, level 3, level 4. So that's n depth. And each node here has 2 children. And each call here for each level will have twice as many calls as the one above it. So because we just now saw the observation here, where there was 8, 4, and 2, and then 1 here, we see that the relationship can be structured into a table. So we actually observe that pattern here, and if we actually add this pattern accordingly, so I'm going to jump back to the tree here. The branches for each one of these nodes, there will always be 2 branches, and the depth of the tree is the levels at which we're going to be. So if I'm just going to illustrate this here is L1, this here is L2, L3, and L4, where L here stands for all levels. So our levels here represents the depth of the tree. So the depth here, being n depth, n here is equal to 4. And we have branches here. So branches equal to 2. And when we formulate our relationship here by adding number of nodes, we get that summation going to be that is going to be order of branches to the power of depth. So for this case, it's going to be O of 2 to the power of n. So for logarithms, the base of the log does not matter, but however for exponents, the base does matter. And that's why I just want to explain there. To compare 8 to the n or 2 to the n or 2 to the n, 3 of the n or 4 of the n, you do not differ by a constant factor. So base to powers does matter a lot when you specify your order. Logarithms, you can just use a standard log, that's perfectly fine because you're just going to define some constant factor. The space complexity of this particular theorem is going to be O of n. And this is because even though we have O of 2 to the power of n nodes in the tree, for any given time, we only have O of n existing regarding the memory use. So you only need O of n memory available for each one of those particular nodes. Alright, so that brings us to the end of our sector lectures, and basically the end of our lectures for today. Are there any particular questions regarding this particular topic that we just saw here? The calls on the tree are each instance of when we have function calls. So remember, this is here when we have f of n minus 1 plus f of n minus 2. Am I correct with this? So these refer to each one of those function calls here because it's a recursion function. So when we go down to f of n minus 1, where we are f of 3, and then when we go to f of n minus 2, we go down to f of 2 according and so forth, as we keep on going. So the calls here are just basically the function calls. I may have dropped there for a little bit. Let me guys know if you're hearing me. If I need to repeat my explanation for the function calls, let me know. Yes, we are doing this basically for the sake of efficiency regarding how fast your code runs, as well as how much memory your code algorithm occupies. This is actually going to be very important when you go into interviews and for any sort of programming that you're doing. So yes, it makes things less time to run, as well as it makes things more efficient using less memory for it to run as well. Right, there were two branches coming from each level here because of the nature of our Fibonacci sequence function. Because we had f of n minus 1 plus f of n minus 2 being added all together. So because we had each one of those nodes here coming in. Oh wait, no, this is a modified version. Whoops, sorry. So this actually was correct. Bad. That's why we had two function calls. Alright, sorry about that. That's why there were two branches coming from each level. Thank you for pointing that out. Right. So because we had f of n minus 1 plus of f n minus 1, we have those two branches here for each one of those. That's why when we have f of 4 here, when we return f of n minus 1 plus of f n minus 1, let's say f n was 4, this is f of 3, add f of 3. So we have an f of 3 here and an f of 3 here. That's why we have two branches coming from each one of those levels. Forgot that was a modified Fibonacci sequence. My mistake, I'm sorry about that. The explanation also carries along for the actual Fibonacci sequence where it was f of n minus 1 plus f of n minus 2. The explanation is the same thing. But the reason why I had it modified is just to explain those branches from each one of those levels in particular. All right. Any further questions? So the small view of the key techniques you'll need to use is that when you encounter a recursive function in particular, you're going to have to end up using the recursive tree to figure out how you go about finding the order. So once you see the recursive tree expanding in some sort of exponent order, you just need to find out what's going to be the depth of the tree and how many branches each one of those nodes have to figure out what's going to be the base regarding that. Because remember, the order here will follow the general terminology here, O of branches to the power of depth. For the iterative functions, you just basically analyze how the for loops operate. So if the for loops are not nested, but they are following in sequential order, you add the orders accordingly to figure out, okay, if they're going to be O of n, if is that they use independent variables, if like the first for loop was A and the second for loop was B, there'll be O of A plus B, accordingly and so forth. If the for loops are nested, it's going to multiply. So if it was n times the outermost loop will run, and then n times the innermost loop will run, that will be O of n by n, which is equal as O of n squared. However, if they use different variables, and there's no relationship between the two of them, if the outermost loop was A and the innermost loop was B, it will be O of A multiplied by B. And that's basically the short gist of the techniques that you'll end up using. It's just basically trying to figure out what's going to be the relationship. And once you find out what's the relationship by analyzing the flow of the code, that basically describes the order of your algorithm altogether. So in our particular case, because we saw the tree here expanding in powers of 2, that's how we knew it's going to be 2 to the power of n, where n is the number of nodes or the number of depth. Sorry, and where n here is the depth of the tree. If it was expanding along a logarithmic function, meaning that if we had it going in reverse, that we had 8, 4, 2, 1, that's how we know that it goes in a log fashion, because it keeps on halving each time. So once you establish your flow of the code here to see how do your function calls operate, as well as how the memory operates as well, respect to n and so forth, you can basically establish what's going to be your time complexity with regards to big O, as well as you can use the same techniques for the space complexity as well. Now, like I said, I'm not going to leave you guys in the dark regarding this. In our tutorial session on Wednesday and next week Monday, you are going to get practice on example problems to see why it is that we get certain orders in particular, and you will get the explanations and so forth. Now, remember, getting to the final answer is what's going to come towards the marks, your approach. Just putting the final answer doesn't really explain that you understand how it's being done. So if I had to allocate a marking scheme for this, let's say if I gave you a piece of code and I asked you guys to find out what's the order, and if it was with 5 marks, the final answer is only going to be one of those 5 marks. Your explanations as to how do you derive to the order is going to be those remaining 4 marks. So you can get the final answer wrong, but if your explanation is spot on, you're still going to get 4 out of that 5 marks. Alright, any further questions? Alright, doesn't seem like we have any further questions. So if there are any further questions, feel free to leave them down in the comments down below, or directly email me and I'll get back to you guys accordingly. So just repeating, in Wednesday's session, which is our tutorial session, we'll be doing live practice on particular code problems that you may encounter in an interview, but analyzing what's going to be the time complexity of these particular parts of codes. And we'll also be doing this practice carrying over into next week's Monday session as well. All of these practice sessions that we're doing here is going to be leading you guys up to your first quiz, which is going to be released on next week Wednesday, as well as your first group assignment, which will be released later on next week as well. So, like I said, if you guys have any particular questions, feel free to email, feel free to leave them down in the comments below. You can find a lot of code snippets to practice on to see if you can figure out order of the code. You don't actually need to know particular operations when it comes to like how the functions and things may be run and so forth. You can just watch the general code and you can be like, okay, you're watching the operator with regards to the loops or the function calls, figure out what's going to happen. But Wednesday session and next week Monday sessions, you're going to get a lot of examples to actually practice on. And I'm going to give you guys the code first for each one of the examples, see if you guys can figure it out. And then I'll give you guys the explanations right after we poll and see what's going to be the answers. Alright, so until Wednesday session, take care, be safe, and I will see you guys soon. Later.